Hi, everyone. Thank you for joining me here today in Paris for this short presentation. I hope you are doing well. My name is Nathan Glazer, and I will be presenting our work on uncertainty-aware multimodal fusion. This work is done in the Ripple lab at Georgia Tech. The fusion of multiple sensor modalities in deep learning has been an active area of research. However, a less explored aspect of such work is robustness to degradations across the input modalities. In this work, we propose an uncertainty-aware fusion scheme to effectively fuse inputs that might suffer from a range of known and unknown degradations. While our uncertainty fusion framework can be applied to different perception tasks, we are especially interested in RGBD semantic segmentation. The problem is to predict dense pixel-wise class labels given an aligned RGB and depth data input. People have explored fusion of different modalities to improve general performance. In the case of semantic segmentation, RGB plus depth data is a common combination. Researchers have found that exploring intermodality interaction at feature level improves performance. Probability level fusion also yields better performance than unimodal models. In audio-visual speech activity recognition, researchers have explored stream weighting using uncertainty with hand-picked thresholds. While feature level fusion is mostly end-to-end learning, probability level fusion is mostly post-processing methods and offers good interpretability, which can be quantified using information theoretic metrics. We want to further expand the research on probability level fusion with a more flexible and automatic framework. We propose uncertainty-aware, noisy OR fusion. Specifically, we analyze a number of uncertainty measures, each of which captures a different aspect of uncertainty, and we propose a novel way to infuse uncertainty to degraded inputs by scaling modality-specific output probabilities. We additionally propose a novel data-dependent spatial temperature scaling method to complement these existing uncertainty measures. Finally, we integrate the uncertainty-scaled output from each modality using a probabilistic noisy OR fusion method. There are many existing works on estimating uncertainty from deep neural networks, such as information theoretical metrics, softmax probabilities, and density estimation. We will primarily focus on information theoretic metrics because they require the least change to a model and have well-developed theory. The issue is that they are on different scales. To make different metrics comparable, we need to normalize them to provide the same measurement of uncertainty. We define a deviation ratio denoted delta, which measures how deviated a test image is from the training examples. Given an input image, we calculate a scalar uncertainty value denoted mu mean for each uncertainty metric. A deviation ratio from each uncertainty metric is calculated by normalizing through a cumulative training mean and variance. Our formulation limits the deviation ratio to be between 0 and 1, with 1 being in distribution and any other number being out of distribution to a different extent. We combine the different ratios into a single scalar, denoted as min deviation ratio, using a min operation because a smaller number implies more deviation. Intuitively, we choose the metric that is most sensitive to the current degradation. Inspired by the results of temperature scaling, we adopt a similar approach to scale the predictions. We multiply the computed deviation ratio with the logits before applying the final softmax function. For example, if the deviation ratio for an image is 1, it is considered in distribution, and the predictive distribution remains the same. If the ratio is less than 1, the image is considered out of distribution, and by multiplying it with the ratio, the predictive distribution is flattened, representing increased uncertainty. This table shows the average deviation ratio for different metrics across various degradations. For each modality, a different min deviation ratio is calculated. In this case, we have RGB and depth. For in-distribution data, both the depth and RGB deviation ratios are 1, indicating perfect conditions. For degraded RGB data, the RGB deviation ratio is less than 1, and the same is true for degraded depth data. We also see that different metrics exhibit different sensitivity to different degradations. Now we introduce a new uncertainty metric, temperature net. Let's start with the failure of existing uncertainty metrics. On the right, 3 information theoretic uncertainty maps are shown. These uncertainty metrics reflect uncertainty at the boundary of classes. However, they yield low uncertainty in misclassified regions due to fog. In other words, they failed to capture spatial degradation caused by fog. We introduced temperature net, TempNet, which captures the spatial degradation. This is the overall pipeline for a single modality. Our framework can incorporate arbitrary sets of modalities. We first extract uncertainty measurements from various metrics and compute deviation ratios for each one. A joint min deviation ratio is obtained through a min operation. Finally, we apply the deviation ratio to the pre-softmax logits and make the output distribution uncertainty aware. TempNet has several advantages. It produces a pixel-wise temperature map that conditions a pre-trained segmentation network in the input of the same modality. For example, the top right image visualizes the pixel-wise temperature map. Darker regions represent higher uncertainty. We also plot the softmax probability of the predicted class with and without the temperature map applied. When we apply the generated temperature map to the output distribution, we can see the gradual decrease in confidence into the distance for the dense foggy area on the lower right. We model the fusion process as a graph where each independent segmentation branch contributes to the final prediction. We view each segmentation branch as an independent expert. An arbitrary number of these experts can be added or removed without affecting the ability to produce complete predictions. The specific model we use is noisy OR. It can approximate conditional probability under the independence of causal inference assumption. Under the independent causality assumptions, the conditional probability distribution can be approximated as a noisy OR operation. Here we list the two independent assumptions. We argue that the individual segmentation networks satisfy these two assumptions because each network can produce complete segmentation with or without the others. We use the AirSim simulator to collect data because it is photorealistic and provides different sensor outputs. During test time, we apply various unknown degradations from this GitHub repo. We compare to various probabilistic fusion baselines as well as state-of-the-art RGBD semantic segmentation networks. Our framework, UNO, outperforms the other compared methods under degraded conditions. We also incorporate state-of-the-art RGBD segmentation networks as additional experts, denoted UNO++, to further improve performance. Here, we show our method, UNO++, alongside state-of-the-art RGBD segmentation networks. Unseen degradation is applied to either the RGB or depth channel. Our method can produce more robust segmentation under various degradations, whereas the other method fails. In summary, we proposed a method to combine several uncertainty metrics and infuse uncertainty to output probability using deviation ratio and uncertainty-aware scaling. Outputs from different modalities are combined probabilistically using noisy OR. We further introduced TemperatureNet to capture spatial degradation. Thanks for listening.